And then we'll zoom over to alcohols. Now, this chapter is the first chapter we've encountered oxygen. Oxygen's got lots of forms, and you're going to see that manifested in the next unit, even bigger than this unit. But the main component of this chapter is going to be the alcohols, but there's also phenols, which is an aromatic alcohol, and ethers. Ethers have no OH group, just an oxygen in them. So the name of the OH functional group is called a hydroxyl group. And there are two types of connections. We can have a aromatic alcohol, like phenol is the simplest one, or we can have an aliphatic alcohol like rubbing alcohol. Now remember, aromatic contains benzene, aliphatic doesn't contain benzene. So an alcohol has an OH group, a ether has a OC group. Excuse me. Now these are some very common examples. Menthol used to be a lot more common than it is now because that's what they used to flavor cigarettes with. They'd have menthol cigarettes. My mother used to smoke those. Ethanol is extremely common and drinking alcohol. And it's the problem with ethanol, it's not as toxic as other alcohols. All alcohols pass through the blood-brain barrier, including sugars. Sugars are alcohols. And other things, but they're mainly alcohols. The problem with ethanol is one, it's readily available, easy to make, and it's not as toxic. So all you get is an adulterated state. But it can lead to death if you drink too much alcohol. Other alcohols related to ethanol, like methanol, that's a one carbon alcohol, causes blindness. You all heard of cholesterol. Cholesterol is kind of a extremely weak alcohol. It's mostly lipid. Okay, so same old routine on this naming. Three parts again. In fact, let's add a, oops. Let's add a methyl group there. So it's got a branch. All right, so first things first, find the backbone that contains the functional group. Okay, so we've got two routes that way. Okay, so we definitely have to include this carbon here. But we can go up or down. Let's just go across. Okay, and that's a 6-carbon backbone. The functional group is an hydroxyl group. That makes it an alcohol. Alcohols have an OL name to them. And in this case, we've got a branch. So that would be 5-methyl-3-hexanol. Or is that the best way to number this? What would be a better way to number this? Well, if we started numbering at this end,
4-methyl.
Okay, so we have a conundrum here. Which is better?
The two methyl,
Which one?
the bottom one.
Well, remember when we talked on Monday about alkenes, I said the functional group numbering predominates, not the branch numbering. So, which has got a lower functional group backbone numbering, the 3-hexanol or 4-hexanol? That would be the better name because the backbone is minimized with a functional group containing the OH. Even though the 5-methanol seems high, but when you look at the process for numbering the backbone, functional group wins out bar none. Now on a test, I would not completely, if you answered 2-methyl-4-hexanol, I wouldn't mark it completely wrong. I would give you partial credit. Because the purpose of me focusing on naming is so you look at the structure more carefully. And by naming it this, you looked at the structure very carefully. Otherwise, you couldn't have come up with that. Okay, so is it clear why the 3-hexanol wins out over the 4-hexanol?
Yes, thank you, Professor.
Sure. And then here's another example, another hexanol. Now, like with double bonds, we can have dienes. With alcohols, we can also have diols and triols, etc. And they'd be reflected using those terms there. Now, as far as the aromatic alcohols go, I'm going to start by talking about benzene again. Benzene is an extremely stable compound because it alternates inside that 6-membered ring. Now, the definition of an alcohol, excuse me, the definition of an acid. I know you're wondering why we're talking about acids. Definition of an acid is, well, there are about 6 ones, but the simplest one is it disassociates a H plus ion. Okay, so if a compound has an H in it, it could be an acid, assuming it disassociates an H plus. Now, the unique thing about phenol, it acts as an acid also. Besides being an alcohol, it's also an acid because now the strength of an acid is determined by how stable this is. If that's very stable, it'll be a stronger acid. Excuse me, if it's unstable, it'll be a very weak acid or not an acid at all. So this is more stable than a normal dissociation from an alcohol because of the ring. And what happens is this charge can be shared throughout the inside of that benzene ring. Hence, this is more stable than a normal hydrogen ion coming off of an alcohol. So phenols are weak acids. So every one of these is a weak acid because they're all a derivative of phenol. Okay, so does that make sense? And again, it's because of this single, double, single, double, single. Because when the charge is here, what happens? It gets distributed again. Very powerful. And you see that a lot in biochemical molecules, like citric acid, which is a triprotic biological acid. Okay, now alcohols can be classified. In fact, your first wet lab is on alcohols. It can be classified depending on where the OH is attached. So we have primary, secondary, tertiary alcohols. And the chemistry of each is slightly different. So it's extremely important to understand why one is primary versus secondary versus tertiary. This will come up again in the beginning chapter in Unit 2 when we talk about aldehydes and ketones, because those can be derived from an alcohol. Okay, so how do you tell the difference? Okay, simply put, primary alcohols are in the end. Okay, secondary has one hydrogen attached. Tertiary has none. Now, these determine the chemistry. When we oxidize something, we lose an electron or hydrogen. So in organic chemistry, you normally talk about losing and gaining hydrogens. In inorganic chemistry, you talk about losing and gaining electrons. So in 305, you probably talked about oxidation is loss of electron, reduction is a gain of an electron. In organic chemistry, it's going to be the loss of a hydrogen or gain of a hydrogen. So if it's on the end, that means it has two hydrogens. So this can be oxidized because it has hydrogens attached to the carbon containing the hydroxyl group. Same here. Tertiary alcohols cannot be oxidized because they don't contain a hydrogen there. So right here, this determines potential for oxidation. And that's going to come into play when we start talking about the reactions of alcohols. Okay, so primary, secondary, tertiary. Primary have two hydrogens and they're always on the end. Secondary is in the middle, has one hydrogen attached, can be oxidized. And the tertiary are also in the middle with no hydrogens attached. Okay, another big difference with alcohols is because of the oxygen, the OH group is very, very, very polar. So that means high boiling points surface tension. They're soluble in water up to C7. And after that, they're insoluble in water. Okay, because the oxygen is attached to a hydrogen, we have hydrogen bonding as one of the intermolecular forces. And it's the strongest intermolecular force. That's why alcohols are so polar. And on alcohols, once this tail starts getting above 7 carbons, the London dispersion forces here take over that strong hydrogen bonding and make this a mostly non-polar molecule. So here you have the alkenes down here. And notice super solubility here of these alcohols. That's a 4-carbon alcohol, 5-carbon. When you hit the 7-carbon alcohol, it no longer is water soluble. You're going to see this 7 number come up again when we talk about solubility of acids. Now, if you think about water, water looks like an alcohol. So it's got a lot of tendencies that alcohols have, like boiling points, water soluble, obviously, high surface tension, and very, very polar. Not mixing well with non-polar groups like alkenes and alkanes. So here's this graph that keeps reoccurring, and we have a line that's missing on this. Which is alkenes. So we've got alkanes, ethers, and alkenes all on this line, well below the alcohols up here. Now this is boiling point, which is indicative of polarity. Now, reactions. Okay. So, to create an alcohol, we already talked about that. That's with an acidic water. And what happens is the water adds across the double bond in an addition reaction. Frequently, there's a mix because it's heterogeneous. Now, as far as an alcohol itself, we can remove the OH group and form an alkene back under high temperature. And again, expect a mix. Slightly less temperature, we form an ether. Because alcohols contain hydrogens next to the OH group, they can undergo oxidation. And we end up forming, if it's a primary alcohol, we're going to form a aldehyde. If it's a secondary, we're going to form a ketone. If it's tertiary, there's no reaction. Okay, so that's the summary of all the reactions with alcohol. Okay, so this is the elimination reaction or dehydration reaction. So this requires energy. Because the alcohol is more stable than the alkene. To make an unstable molecule from a stable one, we have to add energy. In this case, it's going to be heat. So keep that in mind. Whenever we go from something stable to something unstable, it requires energy. Just got a notification, a 12-year-old was shot in Sacramento on K Street. Okay, so again, and this would be this route over here. So we're going to dehydrate an alcohol, and we're going to generate an alkene. Now, dehydration means water has to come off. So we have an OH group, and we need a hydrogen to make up that water molecule coming off. So it's got to be on an adjacent carbon. So that's water there, and that's water there as well. So we can get that water two ways. And this is where the mix comes in, is we can usually get water from more than one place adjacent to that OH group. So for example, if we look at this guy down here, this is 1, 2, 3, 4. So that's a butanol. And okay, so that's butanol. You've got to specify the temperature here. Okay, so there's an H here and an H.
Professor,
Yes.
can we put the OH on the top and it still be the same?
You mean like, oops, no, not like that.
Yeah, in the dip. Yes, there.
Yep, same molecule.
Okay, great.
No
Thank
problem at
you.
all. Good question. Okay, all right. So the bottom line in this particular reaction is we can get water two different ways. We can get it this way. We can get it this way. Okay, this is important now because this is a heterogeneic process. Hetero typically means mixture, and that's what we're going to get. So we're going to get a double bond forming on the right and the left side of that OH group. So if we're using the blue water, the double bond is going to be here. And we're using the red water, it's going to be here. Now, the original location for the OH was here. So basically, have kind of a pivot on either side of the OH group, forming the double bonds. And then we need to figure out which is more stable. So we have our tests, which is Markov-Markov, and symmetry. Okay, so the one on the left, we have 3 hydrogens, 2 hydrogens, 3 hydrogens, 3 hydrogens. So Markovnikov wins there. As far as symmetry goes, well, the double bond is in the middle versus stuck on the end, so the red is more symmetrical. So this would be the more stable of the two. Now, there's another little wrinkle in this particular reaction, is that we can also form, because remember, double bonds are rigid. So we can also form that. This would be cis-2-butane. This would be trans-2-butane. And then this would be 1-butane. So we have, oh, we're going to name this too. So this would be 2-butanol. Okay, so we've named the reactants, we've named the products and conditions. Now this is a little extra. Distinguish between cis and trans. So in other words, I would give you a smiley face if you put down the cis also. With probably a plus 1.2. Okay, so the interesting thing with this particular reaction is if we lower the temperature down to 140, you don't get an alkene because there's not enough energy to get you to an alkene because alkenes are so unstable. Okay. Now, we're going to talk about this particular reaction in Unit 5. This is part of the citric acid cycle, where enzymatically this happens. Enzymes are magic. And what you can do in a test tube versus what you can do with a enzyme is entirely different. Okay, so this is called a mechanism, by the way. You study that in the year-long organic chemistry class. You study mechanisms in a very detailed way. And this is how it actually happens at the atomic level. And I feel this is out of the scope of our class. So we are not going to focus on it. Okay, so what happens at a lower temperature? What do you get? Okay, what happens, we form an ether. So an ether basically connects two, so if you've got um, 140, these two attach. And that's what an ether is. So for example, we take 2 ethanols under those 140 acidic conditions, we end up with an ether. Now to name an ether, there's 2 ways to name ethers. One is the common way, and then the other way is the IUPAC way. That's an ethyl group, so it's a diethyl ether. That's the common way, and that's the way we're going to be naming these. The other way, using the IUPAC, name. Well, this is an ethoxy group. So this would be one ethoxy ethane. That's an X, by the way, ethoxy. But we're going to use the common way, diethyl ether. Okay, so bottom line, lower conditions, the OHs are stuck together. That's the easiest way to form an ether is from two alcohols. And they don't have to be the same alcohol either. It can be methanol and ethanol or methanol and propane. It doesn't really matter. Okay, so okay, now oxidation happens a lot in our world because of the predominance of an oxygen atmosphere. So things oxidize all the time, whether it's losing electrons or losing hydrogens in an organic sense. So this is the oxidation route here on the right in purple. So R is reduction, O is oxidation. Reduction is the opposite of oxidation. So if we are losing a hydrogen in oxidation, reduction means we gain it, which is the opposite of oxidation. Okay, so when we're talking about alcohols and oxidation, there are three routes: primary, secondary, tertiary routes. Because primary alcohols have two hydrogens, it can be oxidized twice, like I was saying earlier. The first time it forms something called an aldehyde. The second time it forms an acid, an organic acid, which is called carboxylic acid. We have a whole unit on acids and fats. If it's an internal secondary alcohol, it can be oxidized once because it has one hydrogen. It goes to something called a ketone. And I'll talk about aldehydes and ketones in a minute here. If it has no hydrogens attached, it can't be oxidized or reduced, actually. So this can be both oxidized and reduced. So this would be tertiary, secondary, primary. And don't forget, you're going to have this on your test, this flow chart. Okay. So alcohols, there's a lot of reactions with alcohols. We can oxidize them, we can also reduce them. We can dehydrate them. lots of different combinations. Okay, so let's look at more detailed primary alcohol oxidation. Again, loss of hydrogens, okay? And the hydrogens I'm talking about are the ones connected to the OH group. Any other carbons, doesn't matter. It's the only ones that count is the carbon directly attached to the OH group. So here we have two hydrogens attached to that carbon with a hydroxyl group on it. That means it can be oxidized twice. Now that's what the O stands for. A generic oxidation. So you can have things like dichromate, lots of different oxidizing environments. But we're just going to say O in parentheses and R, which is the opposite of oxidation. Okay, so the first thing it forms is a double bonded carbon oxygen, and that's the aldehyde. Now, we still have that original carbon with an H, so it can undergo oxidation again. So now we form a carbon oxygen double bond plus a hydroxyl group. And this is what makes an organic acid. And usually it's written like this. I like to write it like this up here, but it's frequently written like this. Okay, so basically aldehydes, they it's very hard to stop this reaction. If you start oxidizing a primary alcohol, it's hard to stop it at the aldehyde. It immediately goes on to the acid. Now, this is how a breathalyzer works for detecting a DUI and a traffic stop. Is using this reaction. What happens? Ethanol is a primary alcohol. And when it's oxidized, you get a color change. And the color change is calibrated as to the concentration of ethanol. The more ethanol, the more intense the color. And you can measure that with a light shining through it. And that's what the little breathalyzers do. A very simple reaction. And by the way, easy to skirt around. For example, if you just washed your mouth out with Listerine mouthwash, Listerine has 40 to 60% alcohol in it. And then you spit it out, and then you take a breathalyzer, you will go off the chart. You'll be up there around 0.3, 0.4. Okay, so this is the reaction of a secondary alcohol. Okay, it can only be oxidized once because it has one H. And you form something called a ketone. Now, ketones have carbon here and a carbon here. An aldehyde has a carbon here, and an H here. Notice there are no hydrogens attached to that carbon anymore. Hence, the oxidation stops there. So when you do your wet lab on alcohols, you're going to be able to tell what kind of an alcohol you have based on whether it's oxidizable or not. If it's not oxidizable at all, like with a tertiary, in other words, no reaction, no visible reaction, then you know that you've got a tertiary alcohol. If you end up with a ketone, you know you have a secondary. If you end up with an acid, you know you have a primary alcohol. Now, I want to talk about ethanol some more. Your body has a way to get rid of alcohol in your body. That's why when you drink, they always give you a timeline. One drink, you should wait an hour and a half to 2 hours before you drive a vehicle, unless you're super sensitive to alcohol, etc. This is how your body gets rid of alcohol. This happens in your liver. The liver has an enzyme in there called alcohol dehydrogenase. What it does, it converts your alcohol in your liver to something called acid aldehyde. The acid aldehyde is further oxidized by something called aldehyde dehydrogenase and converts it to acetic acid, and then you pee it away. Now, if you drink too much, you won't have enough dehydrogenase enzymes to go around. Or if your liver is damaged, or certain cultures have different levels of dehydrogenase in their systems. So that's what determines how much liquor you can hold, are these two enzymes in your liver. So treat your liver nicely. It does a lot of cool stuff. This is one of them. Okay. All right. This is a common oxidation compound. There's a number of them. That's a real common one. It's called potassium dichromate. Okay. So we've got dichromate. This is dichromate now, which is kind of an orangey color. Okay, so what we're going to do, and in here we've got ethanol, primary alcohol. So when we dump this into there, because it's a primary alcohol, an oxidation is going to occur. We're going to convert it to an aldehyde and to an acid. Now, this is the big deal, is whenever an oxidation recurs, the oxidant, in this case dichromate, gets reduced. So you have to have a reduction in oxidation happen simultaneously. No exceptions, because you're transferring hydrogens and transferring electrons from one to the other. So you have to have a donor and a recipient. So what happens is the oxidant changes color in this case. That's this kind of a blue-gray. And again, this is what happens in the breathalyzer test. Same concept. You have ethanol, you dump in, and depending on how much ethanol you have, whether it's dilute, like in your body, or pure, like here, the color difference is proportional to the concentration of the ethanol present. And again, this is similar to what we're going to be doing on our first alcohol wet lab. Okay, and this is what I showed you before. Okay, all right, so that concludes the reactions for alcohol. Oops. Dehydration, high, low temperature. Oxidation, primary, secondary, tertiary. Now, And then to make an alcohol, you can make one via an alkene. Okay, so let's practice this a little bit here. I am super hot. I'm going to turn on my fan. Oh, my dogs are below me at my feet here. Okay, so let's do some reactions. Let's try to make, no, let's not try, let's see, let's, okay. Let's take this butanol, and so this would be 2,3-methyl-2-butanol, and we're going to expose it to some high heat, 140 over in an acidic environment, the sulfuric acid. Okay, so we're looking at it over here. This means we're going to form an ether. So that means we're going to take 2 of these butanols and stick them together at their OH points. Now, in my opinion, the easiest way to do this is we're going to end up with a vertical ether rather than a horizontal ether. And I like to just stack it, okay? So we need to connect up the OHs. So let's draw one. And let's make the oxygen attachment go up. So that's half the ether. The other half is going to be going down. So that's what we make. So what we do on one of them, we're going to flip this OH going upwards instead of leaving it down, and then attach them together. So how will we name this? Okay, well, this is going to be, since we're using the same alcohol, it's going to be a di-3-methyl 2-butyl. We're converting the butanol to butyl ether. Okay, so we got reactants named, conditions, products named. Okay, any questions about this reaction? Whenever you're making ethers, you've got to double it. Normally, whenever you're doing reactions, frequently the backbone is maintained throughout. You're going to see that as a trend, not 100% of the time. And this is an example when it's not 100%. I mean, the backbone is sort of maintained, it's just doubled. But normally, the original backbone and the product backbone are, if not the same, very closely related. So that's the first thing to identify. Then ask yourself, what's happening? Is there an oxidation going on, an addition reaction, an oxidation? Just try to figure out what's going on. Okay. Let's see, where do I want that? Let's see, let's do it over here. All right. Okay, so I have propanol. One propanol, and I'm going to oxidize it. What do I get? Okay, so let's look over here. So propanol is a primary alcohol. So it's going to be able to oxidize 12. So now we're going down to the acid. So I've got a 3-carbon starting point. That means I'm going to end up with first a 3-carbon aldehyde. So that's going to be and Al is for aldehydes. You don't have to, now, for unit 1, you don't have to name the aldehydes because we haven't had them. You can just say aldehyde. Okay, however, because there's still an H there, we're going to continue the oxidation process and convert that into the 3-carbon. So that's 3 carbons, 3 carbons, 3 carbons. Acid. This happens to be propionic acid. Okay, and again, so we have the structure maintained, the backbone. Again, this is a reoccurring theme, this backbone. Kind of, the carbon backbone kind of stays with the processes. Is everyone okay with this reaction? You guys are awfully quiet today.
Yeah, I just need to practice this a little more.
Okay. Well, I mean, yes. We just started alcohols today. So it's going to be, you know, you're going to put a lot of time in this weekend for that test. And alcohols just complicate what we've already been through. Now, think back on alkanes. Remember we just had 2 reactions? You know, combustion, and combustion still comes into play. Alcohols burn quite nicely. Aldehydes burn quite nicely, and acids burn quite nicely. So combustion is always there as a reaction. So for example, if we had I said spark, you'd end up with this. So combustion on any organic compound usually works fine. Okay, so let's practice some more. Let's see now here. Okay, so propene. How can I make propene? Okay, propene is an alkene. So we go back to our good old flow chart. Well, let's use the other one. More comprehensive one, okay. This one here. So there's this way to make an alkene, and this way to make an alkene. Two ways to make an alkene. Now notice, to make an alkene this way, you can only do it via enzymes biochemically, which is okay to put in your problem. Just make sure you mention oxidation via biochemistry or enzymatically or something like that. So we're going to make it this way here, down here. Okay, so we've got a 3-carbon backbone. That means we start with a 3-carbon something. Okay, and what do we start with to get an alkene? And we start with an alcohol. Now, there are two ways there are two 3-carbon alcohols. And now remember, when you're dehydrating, we need high temperature in an acidic environment. Okay, so whenever we do this, we have to pull off water. There's an H here. So here's water one way. So that'll give us a double bond here. The other way is this one up here, which would also pull off. Let's do water a different color. Yeah. There's an H there, and there's an H there. So both of these are going to yield a 3-carbon alkene in the 1,2 position, or the 2,3 position. But because this is a 3-carbon, it ends up being, so this is in the 2,3 position. This will be the 1,2 position. Here we have the 1,2 position. So starting with either one of those will give you propene. Now, do I have to say 1 propene? Or can I leave it just plain old propene? Well, there's only one way it's propene. There's no other options. So you may put it down as 1 propene to be consistent, or you can leave it off. Frequently, textbooks will leave it off. I like for students to put it in so that it's consistent with naming. Okay, so we need to name the reactants. So in this case, this is going to be 1 propanol. This is going to be 2 propanol, or isopropyl alcohol, or rubbing alcohol. So that's a UPAC common. Okay. Are you guys okay with this reaction? So this one is I ask you, how do I make this? And then you always use your flow chart. Always use the flow chart. I really stress that throughout the last couple decades I've been teaching this class. And students, after Unit 1, they really start to depend on that flow chart. Because each time we add a new unit, we add to that flow chart. So it keeps getting more and more detailed. Okay, any questions about this guy? All right, so let's do, I'm going to touch upon this right now before we, okay, so this is a question. Okay, so how do I make this starting from that? Okay, so this is a ketone. How do I make a ketone? Well, right up here, it says we oxidize a secondary alcohol. This is not a secondary alcohol. This is an alkene. So there's no way to go directly, the key word here is directly, from an alkene to a ketone. So we need an intermediate step. So to get the ketone, we need a secondary alcohol. Can we make a secondary alcohol from an alkene? So I'm going to modify this reaction and take the cyclics out. So that's a ketone. And I want to make it from that. Okay, so for a ketone, we need a secondary alcohol. Oxidizes secondary alcohol, gives us the ketone. However, we don't have a secondary alcohol, we have a alkene. So can we convert the alkene to an alcohol? Yes, we can. All we need to do is add acidic water. So if we add water and acid, we can create secondary alcohol. So this is called a multi-step synthesis. Multi-step synthesis. Now, this example uses cyclic, and I think that confuses the issue. So we're going to do one that's non-cyclic. Okay, so let's look at this now. We're going to, this would be an addition reaction. This is going to be an oxidation. Secondary alcohol. Okay, so we're going to add water across that double bond. So we start with this guy. The water is going to add here and here. And it's going to end up generating a no mix products. So we gotta name this 1, 2, 3, 4. So that's a 2-butane. And it's water, acidic water mix. So we're gonna end up with this plus this, which is the same molecule. You just flip it. So in this case, there's no mix. Normally we would have a mix. I mean, it's sort of a mix, but the mixture ends up being identical molecules, so it isn't a mix. Okay, so let's leave this uncomplicated. Okay, so now we have a secondary alcohol. So we have 2-butanol. Okay, now we've got the secondary alcohol. Now we can oxidize that, and that'll give us the ketone. Okay, so what we're going to do now is we are going to oxidize it, and that will give us that ketone. Which is the same as this guy up here, just flip left to right. So that's a multi-step synthesis. Now, I'll frequently put these on the tests for extra credit. Now, this is what a typical organic chemist has to do. This is called a precursor. This is a precursor to that. Precursor. So does this process make sense? You ask yourself, can I go in one step? If the answer is no, then you have to create the intermediate steps. Today is a dry lab. Okay, are questions about that multi-step process? Okay. I'm going to talk a little bit more about some general alcohols. Methanol is frequently a byproduct of moonshine. Moonshine is you take frequently fruit, potatoes or some source of starch, barley, etc. You ferment it, and then you ferment it, and then that creates ethanol, methanol, and a bunch of other junk. But those are the two primary things it produces. Okay. Like lightning or moonshine, blindness. Methanol will make you blind. So that's the risk moonshiners make when they make bad booze, is the distillation process, they don't get pure ethanol. They get a mixture of methanol and ethanol. And they have different boiling points. And that's where, if you have a good still, you can actually dial in the correct temperatures and stuff. And you won't get that deadly mixture of methanol in your ethanol. During World War II, submarines carried torpedoes, and a torpedo's got a gyroscope in it, which keeps it going straight. And the gyroscope is a spinning top going very fast, probably 15,000, 20,000 RPM. It goes very fast. And that's what keeps the torpedo from diverging. And the spinning gyroscope is encased in methanol. Submariners found out that you can drink methanol and it'll get you drunk and blind. The blindness doesn't come till later. So at the end of World War II, there were a lot of blind sailors that used to be submariners because they were drinking methanol from the torpedoes. This is a true story too. So anyway, I had a couple buddies that were hobbyists, and they would distill their own booze, and I always say, it's a tough way to go. Okay, again, alcohols in general are toxic. Ethanol is the least toxic. I was saying at the beginning of this lecture today. It's the least toxic, and all the alcohols can go through the blood-brain barrier, getting to your brain. So what happens is the ethanol gradually poisons your brain. Not as badly as methanol, which it poisons it really fast, making you blind. Okay, so let's see here. Now, rubbing alcohol is, as you all know, it's pretty common, really easy it's cheap. And you can get it in various concentrations. Glycerol is used frequently as a byproduct of making soap, for example. And we're going to be making soap. I think it's the third wet lab. We'll be making soap, and you'll be able to take it home at the end of the semester. Antifreeze is an alcohol, and that's why it's frequently people use to kill animals with antifreeze. We had a recent killing off of some stray cats about 3 years ago when I first moved in. This one person ended up moving because people found out they were poisoning cats. And well, anyway, they became very unpopular, and it was not a good place to live for them in this place, being so unpopular. Anyway, and because it's similar to a sugar, it's sweet. So cats just lap it up. Dogs too. Kills them both. And biologically, there's a whole bunch of important alcohols. It's very common, ubiquitous, to see an alcohol or hydroxyl group on a biochemical molecule. They're all over the place. So it's a very, very, we're going to see in the next unit 2, carbohydrates have tons of them. Glucose, for example, has 6 hydroxyl groups. Fructose, 6 hydroxyl groups. Mannose, 11 hydroxyl groups. So lots and lots and lots of hydroxyl groups. A very important functional group. Okay, so that is it for today. I would encourage you, are there any questions? Now today for the Wednesday lab group is a dry lab. I would encourage you, of course, to attend. I also have small whiteboards for you. If you'd like to use one of those, you can form a group in the lab, or you can go out in the hallway and sit at a table with a whiteboard. Any of those work fine for me. I'll be there, of course, to answer questions.
Professor?
Yeah.
I have a question. You said there are gonna be extra credit questions on the exam.
Yes. It'll be a,
How would you say, or just one?
there'll be one, and it'll be a multi-step synthesis. You know, the one example I gave you. This guy here.
Okay, okay. And
Multi-step.
you also said that the exam is next Wednesday for us Wednesday lab people, right?
Yes,
Okay.
Yeah.
Thank you.
now normally, not normally, I always do it this way. The Wednesday test is gonna be different than the Monday test. Just FYI. Okay, what I want to do is real quickly show you practice. And I frequently go over this, I just want to repeat it. Files, Unit 1, worksheets. This is a really good way to study for the tests. Not so much the Lewis dot, but these ones that say organic, week 1, week 2, etc. This would be a good way to practice. And it goes all the way through alcohols and a little bit of aldehydes and ketones, which I wouldn't recommend you doing till Unit 2.
Wait, so Professor, you said not to do week 8 aldehydes.
Correct,
Okay.
correct. In fact, I'm gonna move those to, oops, let's see. Well, I'm thinking about it, I want to move those to Unit 2. Oh, they're already there. Oh, just replace. Okay, so no more aldehydes and ketones. All right, anyway, these would be really good practice, and I do provide the answers as well. Okay. I had a Galena in my class up in Washington.
That's pretty cool. Now you have another one.
I know. I was thinking that too. She was a really good student. She, gosh, she had like 4 or 5 kids and she was single and, oh, I don't know when she slept. It was unreal.
Wow. Well, hopefully I can be a good student, especially on that exam.
Yeah, and look over the practice exams too. I'll give you an idea of length.
Yeah, yeah. Thank you so much.
Okay. If there are no more questions, I'm going to end this. And I guess there's a class, a 305 class, up into 2:45 in the lab. So we won't be able to get in the lab till, basically 5 till. It's gonna be a pain when we start doing wet labs, but anyway, it is what it is, so. Okay,
Professor, so it's a dry lab today?
yes, dry lab today.
Okay.